Hi everyone, this is Maths for Uni. This is question 1G from MAT 2019. The question says, let A, B and C be strictly greater than 0. The equations log A of B equals C, log B of A equals C plus 3 over 2, and log base C of A equals B. A, specify A, B and C uniquely. B, specify C uniquely, but have infinitely many solutions for A and B. C, specify C and A uniquely, but have infinitely many solutions for B. D, specify A and B uniquely, but have infinitely many solutions for C. Or finally, E, have no solutions at all for A, B and C. So first we have these logarithm equations, log base A of B equals C, log base B of A equals C plus 3 over 2, and log base C of A equals B. And in general, logarithm equations we're a little bit unfamiliar with, and so it's worth inverting them and forming exponential equations. If we start with our first one, which is log base A of B equals C, and we think about what function we could apply to both sides in order to remove the logarithm, then we recall that A to the power of something is the corresponding inverse function to the log base A, and so we take this equation and we raise both sides with A, and we have log A to the power of log base A of B equals A to the power of C, i.e. we have our LHS equals RHS becoming A to the LHS equals A to the RHS. But then, because we have the exponential and logarithm with the same base A, these functions will cancel, and so we get B equals A to the power of C as our exponential equation. We can do the same with the second and third, so again this one here gave us B equals A to the C. Hopefully you can see how this rearranges that logarithm equation and apply the same technique to the next two. I encourage you to pause the video and take a quick go at that, but if you're still here, then we have from this that A equals B to the power of C plus 3 over 2, and from this one that A equals C to the power of B. And so we now have these three exponential equations. We want to find how many solutions these equations have, or rather the original equations have, for A, B and C. And so it's worth trying to combine these equations and see if we can find, say, unique solutions for the values A, B and C. If we take a look at the first two equations, which I will write down again, we have B equals A to the C, and we have A equals B to the C plus 3 over 2. We can combine these equations and in the process eliminate A if we raise both sides of this equation to the power of C, because then we'll have an A to the C over here, which we can eliminate with the A to the C over here. So if we do that, then we get A to the C equals B to the C times by C plus 3 over 2, due to how powers work when you multiply them together. And again, now we can eliminate this A to the C using the fact that B equals A to the C from this equation. Therefore we get B on the left hand side from this B here is equal to B to the power of c times c plus 3 over 2 from the right-hand side over here. This is a rather nice equation, because we have b to the power of something, i.e. b to the power of 1 over here, equals b to the power of something else. And because we have exponential functions which are in general injective, this means that 1, i.e. the power on the left-hand side, must be equal to c times c plus 3 over 2. Now, before we proceed, I mentioned the word injective. You may have heard this in the phrase of 1-to-1 for a certain function, but in fact, this exponential, or rather these exponentials on both sides, are not injective if b is equal to 1, because we then have the exponential function 1 to the power of x, which is just a straight line with constant value 1. This is not injective because for all values of x, 1 to the x is equal to 1. However, we are precluded from having b equals 1 because of our original situation. Namely, we have a logarithm involving a base of b, and it doesn't make sense to have a log base 1 precisely because that same function, 1 to the power of x, is not invertible. Again, there are plenty of, i.e. infinitely many, values of x such that 1 to the x is the same value, 1, and therefore it cannot be invertible, and therefore the corresponding logarithm cannot exist. Hence, we cannot have b equals 1 from our original problem, and therefore we can be sure, because also b is positive from the original setup, that we have injective functions from the exponentials, and this means we can set the powers to be equal. The nice thing about this is that this is a quadratic equation. We have, by rearranging, c squared plus 3 over 2c minus 1 equals 0. Now, if we factorize this, we can have c plus 2 and then c minus 1/2. This gives us two solutions, namely c equals minus 2 or c equals 1/2. However, c, we were told, has to be strictly greater than 0, and therefore the only solution for c is c equals 1/2, i.e. we have a unique solution for c. This rules out some of the answers. For example, we cannot have the answer D, and we kind of can't have the answer E as well. However, we need to be careful about E, because we may have a solution for C, but we might not have any solutions at all for A and B. And in that sense, if that were to occur, then possibly E might be correct. Now that we've got the particular value of C, we can then proceed to try and find equations relating A and B. Recall that our original equations in exponential form were b equals a to the c, a equals b to the c plus 3 over 2, and a equals c to the power of b. However, now that we've fixed the value of c, these two equations are identical, because we set them equal, eliminated a, and then found the value of c. And so we only need to consider one of these equations, and say we can get rid of that one there. Putting in the particular value of c that we found, i.e. 1/2, this gives us that a equals b squared from this equation here, and that a equals 1/2 to the power of b from this equation here. we now need to find out how many solutions there are for a and b using these equations. And the fastest way to do that is to sketch out these curves in the BA plane, i.e. we have one axis here, with B and A. The 1/2 to the B is going to look something like this, asymptoting to 0, and then the B squared will look something like this. It's very important because of how exponential functions work that this exponential is in fact growing a lot faster really than this quadratic, at least as b goes towards negative infinity. And so there is no solution on this side. It's worth having those thoughts in mind, otherwise you may have thought that there is a solution on this side if you have drawn it badly. However, there is indeed a solution on this side for positive b. And as we see from how the functions increase for the quadratic and decrease for the exponential, that there is only one solution for a and b. And therefore, there is only one solution for a, b, and c because c is unique with 1/2 as its value. And therefore, there is exactly one positive solution. We need to be careful about that because we were told that A, B, and C were strictly positive. And so we could have only considered solutions in this quadrant here. But either way, we have unique solutions for A, B, and C. And so the answer must be A. If you've enjoyed this content, then please consider liking and subscribing, as well as checking out our full Udemy course, of which the link is in the description. Thanks for watching, and goodbye for now.